Picture this: what if I told you that right now, all around you, even in the emptiest corners of the universe, there's a hidden ocean of energy so powerful it could rewrite the laws of physics as we know them. This isn't science fiction. It's the quantum vacuum, the very fabric of reality itself, a mysterious void that's anything but empty. Beneath the surface of what seems like nothingness lies a swirling sea of particles popping in and out of existence, defying logic, bending space, and holding secrets that could unlock the deepest mysteries of the cosmos. Think of the quantum vacuum as the ultimate illusion. At first glance, it's pure stillness, a perfect, undisturbed nothing. But zoom in closer and you'll find chaos. Virtual particles flicker like ghosts, energy fluctuates wildly, and forces we barely understand dance in the shadows. Scientists call it zero-point energy, but there's nothing zero about it. This invisible realm hums with unimaginable power, whispering clues about dark energy, the birth of universes, and even the possibility of warp drives. It's a place where the rules of our everyday world break down and the impossible becomes possible, and that's just the beginning. Over the course of this journey, we'll uncover 30 of the most mind-bending mysteries hidden within the quantum vacuum. Phenomena so strange they'll make you question everything you thought you knew about reality. From the enigmatic Casimir effect to the shocking implications of vacuum decay, each discovery peels back another layer of this cosmic puzzle. So if you're ready to explore the edges of human knowledge, to stand at the frontier where science meets speculation, then let's dive in, because the quantum vacuum isn't just empty space. It's the most fascinating, least understood force in the universe, and its secrets are waiting to be revealed. If the quantum vacuum were truly empty, it would be the most boring place in the universe. But look closer, and you'll witness a spectacle more chaotic than Times Square at midnight, a frenzy of particles and energy appearing and vanishing in the blink of an eye. These are vacuum fluctuations, the quantum equivalent of a magic trick where something comes from nothing over and over again. At this microscopic level, the void is alive, crackling with temporary particles that borrow energy from the universe, exist for mere fractions of a second, then vanish without a trace. It's as if the vacuum itself is seething with restless creativity, refusing to sit still. The reason behind this madness lies in one of quantum mechanics' most fundamental rules, Heisenberg's uncertainty principle. In simple terms, this principle tells us that at the tiniest scales, nature itself is undecided. You can't pin down both the position and energy of a particle with perfect certainty. The more you try to measure one, the fuzzier the other becomes. This isn't a limitation of our tools, it's baked into reality. And because of this inherent cosmic uncertainty, empty space isn't allowed to be completely empty. Instead, it becomes a bubbling cauldron of temporary particles, popping in and out of existence like fleeting fireflies in the dark. This wild behavior shatters everything classical physics taught us. In Newton's orderly world, things stayed where you put them. Energy was conserved, particles were solid, and nothing just appeared out of thin air. But quantum mechanics laughs in the face of those rules. Here, energy can briefly materialize from nowhere. Particles wink into existence long enough to interact before dissolving again, and the very idea of nothingness falls apart. Even in the deepest voids of intergalactic space, where temperatures hover just above absolute zero, the vacuum is never silent. It hums with this quantum static, a background fizz that physicists call zero-point energy, proof that nature abhors a true vacuum. And these fluctuations aren't just theoretical curiosities, they have real, measurable effects. The Casimir effect, for example, occurs when two metal plates placed extremely close together in a vacuum are pushed together by the sheer pressure of these virtual particles dancing outside them. It's as if the universe is constantly trying to fill the void, and when space gets too tight, even ghostly particles can't squeeze in. This bizarre phenomenon has been confirmed in labs, proving that what happens in the quantum vacuum doesn't stay there, it reaches out and nudges the world we can see. Every second, trillions of these fleeting interactions are happening all around us, invisible yet undeniable, rewriting the rules of what we thought was possible. One of the most jaw-dropping proofs that vacuum fluctuations aren't just theoretical comes from a deceptively simple experiment, one where scientists measured the invisible push of nothingness itself. Picture two ultra-thin metal plates placed so close together you could fit fewer than 1,000 atoms between them. In classical physics, nothing should happen, just two silent, motionless sheets in empty space. But in reality, something extraordinary occurs. The plates shudder and snap together as if pulled by an unseen hand. This is the Casimir effect in action, a phenomenon so strange it feels like magic, but it's pure, unfiltered quantum reality. What's really happening between those plates is a cosmic tug-of-war. Outside them, the quantum vacuum buzzes with infinite virtual particles, flickering in and out of existence in a chaotic dance. But inside that narrow gap, there's barely enough room for even the tiniest wavelengths of these fluctuations to form. The result, more pressure pushing in from the outside than exists between the plates, creating a net force that squeezes them together. It's like trying to clap underwater. The resistance from the liquid is stronger than the empty pocket between your hands, except here, the liquid is the seething energy of space-time itself. This eerie force was first predicted in 1948 by Dutch physicist Hendrik Casimir, but it took half a century for technology to catch up. Today, ultra-precise instruments can measure this phantom push down to scales smaller than a virus. The implications are staggering, because if empty space can exert real, detectable forces, then the quantum vacuum isn't just background noise. It's an active player in the universe, shaping reality in ways we're only beginning to understand. Some researchers even speculate that similar effects might explain dark energy, the mysterious force accelerating the expansion of the cosmos. Could the same quantum whispers nudging those metal plates also be driving galaxies apart? Yet for every answer the Casimir effect provides, it also deepens the mystery. Why does the vacuum's energy appear infinite in calculations? A mathematical absurdity that suggests our theories are still missing something profound. If we could somehow harness these fluctuations, would they offer limitless energy, or are they forever locked away by quantum rules? And most unsettling of all, what if the vacuum isn't stable? Some theories suggest it could exist in different states, like phases of matter. A sudden shift might rewrite the universe's fundamental constants overnight, turning all matter into something unrecognizable. The more we probe these invisible ripples, the clearer it becomes the quantum vacuum isn't just part of reality. In many ways, it is reality, and we're only beginning to decode its language. Imagine a cosmic battery hidden in the fabric of space itself, charged with enough energy to power entire civilizations, if only we could tap into it. This is the promise and paradox of zero-point energy, the infinite reservoir of quantum fluctuations simmering beneath the surface of the vacuum. According to quantum field theory, even at absolute zero, the temperature where all classical motion stops, the universe refuses to sit still. Particles jitter with residual energy, like an engine that never quite turns off, and the numbers behind it are staggering. Calculations suggest that in every cubic centimeter of empty space, there's enough zero-point energy to boil all the oceans on Earth, yet we can't touch it. Not yet, anyway. The reason lies in one of physics' most frustrating puzzles: renormalization. When theorists try to sum up all the infinite energy contributions from these vacuum fluctuations, they hit a mathematical brick wall. The equations explode into nonsensical infinities, as if the universe is scribbling error messages across the cosmos. To make progress, physicists use a workaround called renormalization, where they mathematically subtract these infinities to reveal finite, measurable quantities. It's like balancing a checkbook by crossing out the unpayable debt effective for predictions, but it leaves us with a haunting question. Is this energy real or just a quirk of our incomplete theories? Even stranger is how zero-point energy collides with cosmology. In the late 1990s, astronomers discovered that the universe isn't just expanding, it's accelerating, driven by something called dark energy. At first glance, zero-point energy seems like the perfect culprit, but there's a problem. When you compare the predicted energy density of the quantum vacuum to the observed strength of dark energy, the numbers disagree by a factor of 1 followed by 120 zeros. It's the worst mismatch in scientific history, like expecting a candle's glow and measuring the heat of a billion suns instead. This cosmological constant problem remains one of physics' greatest unsolved mysteries, a glaring clue that we're missing something fundamental about how space, energy, and gravity intertwine. Could the key lie in undiscovered physics? Some theorists propose that unknown symmetries or extra dimensions might cancel out most of the vacuum's energy, leaving behind the faint whisper we call dark energy. Others suggest the vacuum isn't uniform, that what we perceive as empty space is actually a patchwork of fluctuating energy densities, averaging out to the delicate balance we observe. Whatever the answer, the implications are profound. If the vacuum's energy were even slightly stronger, galaxies would have torn apart before life could form. Slightly weaker, and the universe would have collapsed in on itself eons ago. It's as if the quantum vacuum has been fine-tuned with impossible precision, leaving us to wonder, was it luck, necessity, or something beyond our current understanding? For now, zero-point energy remains tantalizingly out of reach, a cosmic mirage shimmering just beyond the horizon of our theories. But the pursuit of its secrets has already reshaped science, from the Casimir effect to black hole thermodynamics. And who knows, one day we might uncover the Rosetta Stone that deciphers the quantum vacuum's hidden language, turning infinite energy from a mathematical curiosity into the ultimate power source. Until then, the vacuum hums silently, its mysteries echoing through every atom of our existence. There's a cosmic tug of war happening right now, stretching the universe apart at an ever-increasing rate, and the culprit might be hiding in the quantum vacuum itself. Dark energy, the mysterious force behind this accelerating expansion, behaves eerily like zero-point energy. Both permeate every corner of space, both exert a kind of negative pressure, and both seem to arise from nothingness. At first glance, it's tempting to connect the dots. Could the restless energy of the vacuum be the very thing pushing galaxies away from each other? But when physicists crunch the numbers, reality throws a curveball so massive it nearly breaks the math. The discrepancy is almost comical in its enormity. If you calculate how much energy the quantum vacuum should contain based on known quantum fields, you get a number roughly 1 followed by 120 zeros larger than what we observe dark energy to be. That's like expecting a single grain of sand and instead finding a sandbox the size of the observable universe. Such a colossal mismatch isn't just a minor error. It's a screaming red flag that something fundamental is missing from our understanding. Either we've misjudged how vacuum energy behaves on cosmic scales, or dark energy is something else entirely, a shadowy player we haven't even identified yet. Some theorists argue the answer lies in cancellation effects, a cosmic balancing act where positive and negative contributions from undiscovered particles or fields almost perfectly offset each other, leaving behind only the faintest residue we call dark energy. Others propose more radical ideas like vacuum energy, leaking into extra dimensions or varying across space like an invisible tapestry. Then there's the unsettling possibility that dark energy isn't constant at all, that it's evolved over time or interacts with matter in ways we haven't detected. Each hypothesis twists the puzzle into new shapes, but none yet fit perfectly. What makes this mystery so electrifying is the stakes. dark energy doesn't just nudge the universe, it dominates it, making up nearly 70% of all the energy in existence. If the quantum vacuum is somehow its source, then unlocking this connection could rewrite physics. Imagine discovering that the same ghostly particles flickering in lab experiments also hold the leash on the fate of galaxies. Yet if the two are unrelated, the implications are even wilder. It would mean there's an entirely separate layer of reality we've yet to comprehend, a force operating in the shadows of the quantum world. One thing's certain, the vacuum isn't playing by the rules we thought we knew. Whether it's hiding dark energies, secrets, or guarding something stranger, its whispers are the closest thing we have to a cosmic Rosetta Stone. Every flicker of virtual particles, every tremor in the Casimir effect could be a clue waiting to be deciphered. And with each new discovery, we inch closer to unraveling the greatest magic trick the universe has ever pulled. Virtual particles might sound like the stuff of fantasy fleeting phantoms that exist just long enough to shape reality before vanishing again. But these quantum apparitions are very real, and they're the invisible architects behind some of the universe's most fundamental forces. Picture two electrons repelling each other. In classical physics, we'd say it's like two magnets pushing apart, but quantum mechanics reveals something far stranger. The electrons aren't just magically sensing each other's presence, they're constantly exchanging a flurry of virtual photons, particles that blink into existence, carry the electromagnetic force, then disappear before they can be measured directly. It's as if nature prefers to work through intermediaries, even if those intermediaries break the usual rules of existence. To visualize this, physicists use Feynman diagrams, simple sketches that map out particle interactions like cosmic flowcharts. In these diagrams, virtual particles appear as internal lines, fleeting messengers shuttling between stable particles. A photon emitted and absorbed between two electrons might seem like a scribble on paper, but it represents a profound truth. What we perceive as a seamless force is actually built from countless microscopic handoffs, a game of quantum hot potato played at unimaginable speeds. These virtual exchanges aren't limited to electromagnetism. They underpin the strong nuclear force binding quarks, the weak force behind radioactive decay, and even gravity, if theorists can ever reconcile it with quantum theory. But virtual particles aren't just force carriers, they also hold the key to one of the universe's most dramatic phenomena, black hole evaporation. Here's where things get truly mind-bending. According to Stephen Hawking's groundbreaking work, the vacuum near a black hole's event horizon isn't quiet. Pairs of virtual particles constantly pop into existence, as they do everywhere in space. Normally, these pairs annihilate each other almost instantly, but near a black hole, one particle might fall in while the other escapes, stealing a tiny amount of the black hole's energy in the process. Over eons, this trickle of escaping particles hawking radiation could cause the black hole to slowly shrink and vanish. It's a staggering idea, the mightiest traps in the cosmos undone by quantum whispers from the vacuum. Yet virtual particles raise as many questions as they answer. If they're borrowing energy to exist, how does the universe balance the books? Quantum mechanics allows these temporary violations of energy conservation, but only within the tight constraints of Heisenberg's uncertainty principle. The more energy a virtual particle borrows, the shorter its lifespan, like a cosmic payday loan with an unforgiving deadline. This delicate dance ensures that, on average, energy is conserved, but it leaves us wondering, are these particles truly unreal, or do they represent a deeper layer of reality we haven't yet grasped? Some interpretations suggest virtual particles are more than mathematical tools. They could be the quantum vacuum's way of testing every possible path between interactions, a probabilistic frenzy where reality itself is negotiated moment by moment. Others argue they're merely artifacts of our equations, convenient fictions that help us model forces without physical reality. Either way, their effects are undeniably tangible. From the glue holding atoms together to the slow death of black holes, virtual particles prove that even emptiness is alive with possibility, a reminder that the universe's quietest corners are often its most astonishing. The quantum vacuum's most audacious magic trick isn't just spontaneous particle creation, it's the ability to conjure light from sheer motion, a phenomenon so bizarre it sounds like science fiction. Enter the dynamical Casimir effect, where scientists don't just observe virtual particles, they force them into reality. Picture a mirror vibrating faster than a hummingbird's wings, approaching speeds where relativity starts to warp the rules. At these extremes, something extraordinary happens. The mirror's movement becomes so violent it literally shakes photons into existence from the void. It's as if emptiness itself is a cosmic vending machine, and rapid motion is the coin that makes real particles drop out. How does this work? Think of the vacuum as a quiet pond. Virtual particles are like faint ripples that normally cancel each other out, leaving the surface smooth. But if you drag a paddle through the water at blinding speed, those ripples can't recombine fast enough. They break free as real waves. In quantum terms, the mirror's extreme acceleration distorts the electromagnetic field around it, preventing virtual photon pairs from annihilating each other. Some escape as detectable light, transforming from mathematical ghosts into tangible energy. The catch: you'd need to vibrate a mirror at nearly the speed of light to see this macroscopically, a feat beyond today's engineering. Yet physicists found a loophole. Instead of mechanical mirrors, they used superconducting quantum interference devices, or squid circuits so sensitive they can mimic a mirror's movement by switching their electromagnetic properties trillionths of a second. In a groundbreaking 2011 experiment, researchers at Chalmers University of Technology pulsed these circuits at gigahertz frequencies, effectively shaking the quantum vacuum. The result: microwave photons emerged from nowhere, matching predictions perfectly. It was the first lab-made proof that you could mine light from emptiness itself, a validation that blurred the line between virtual and real particles. The implications ripple across physics. If we can convert motion into particles, could the same mechanism explain energy creation in extreme cosmic environments? Some theories suggest the dynamical Casimir effect might occur near neutron stars or in the early universe, where spacetime itself writhed with violent fluctuations. Others wonder if advanced civilizations might one day harness this effect, turning mechanical energy into light or even extracting net energy from the vacuum, though quantum thermodynamics puts strict limits on such dreams. But perhaps the most tantalizing clue lies in what this experiment reveals about reality's flexibility. The fact that virtual particles can be promoted to real ones suggests they're not mere calculation tools, they're latent possibilities waiting for the right conditions to step into existence. It's as if the universe keeps a ledger of potential particles, and extreme motion lets us cash in on that debt. And with every photon coaxed from the void, we get closer to answering the century-old question: is the vacuum truly empty or just pregnant with possibilities we're only beginning to unlock? The universe has a secret ingredient, an invisible molasses that clings to every particle, slowing them down just enough to give them the gift of mass. This is the Higgs field, a cosmic presence so fundamental that without it, atoms would zip around at light speed, never clumping together to form stars, planets, or us. Unlike the chaotic frenzy of virtual particles in the quantum vacuum, the Higgs field isn't a temporary flicker. It's always on, permeating every corner of space with a steady, unwavering value. Imagine walking through an endless field of wet sand. Even when the surface looks undisturbed, your feet sink in slightly with every step. That's how particles interact with the Higgs. They're constantly slogging through this invisible resistance, and that struggle is what we experience as mass. But here's the twist: the Higgs field shouldn't exist like this. In most quantum fields, the default state is zero, like a calm lake with no ripples. The Higgs defies expectations by being stuck in a non-zero state everywhere, like a lake frozen mid-wave. This peculiar trait, called spontaneous symmetry breaking, is why particles have mass at all. Picture a crowded party where everyone is evenly spread out until a celebrity walks in. Suddenly, the symmetry breaks as people cluster around the star. In the early universe, something similar happened. As temperatures cooled, the Higgs field chose a non-zero value, and that decision gave rise to the mass hierarchy we see today. Electrons, quarks, even the Higgs boson itself, their masses are just harmonies played on this cosmic instrument. Yet the Higgs raises a provocative question. If one hidden field can shape reality so profoundly, could others be out there, still undetected? Some theories suggest the Higgs might have cosmic cousins, fields that don't grant mass but influence dark matter, dark energy, or even time itself. The action field, for instance, is a hypothetical candidate that might explain why the universe has so little antimatter. Others propose quintessence, a dynamic field driving the acceleration of cosmic expansion. These aren't wild guesses, they're informed speculations backed by gaps in our equations, like detectives reconstructing a suspect from fingerprints left at the scene. The hunt for these hidden fields is anything but abstract. Particle colliders like the Large Hadron Collider don't just smash protons, they're vacuum archaeologists sifting through debris for clues about the Higgs's secrets. Subtle anomalies in its behavior could hint at interactions with undiscovered fields. Meanwhile, ultra-precise experiments measuring the electron's dipole moment, a tiny asymmetry in its charge distribution, might reveal whispers of new fields tweaking particles at scales a billion times smaller than an atom. What's mesmerizing is how these ideas reframe the vacuum. We used to think of it as a blank stage where particles perform. Now it's more like an orchestra pit, humming with invisible instruments whose music dictates the laws of physics. The Higgs field is just the first chair we've identified, but the symphony is far richer, its full score still waiting to be uncovered. And with every discovery, we're not just learning about the universe's machinery, we're decoding the very conditions that made our existence possible. After all, if the Higgs value were even slightly different, atoms might never have formed, and the cosmos would be a sea of featureless light. The vacuum, it seems, is anything but empty. It's the silent architect of reality itself. What if the universe is sitting on a quantum time bomb, one that could detonate at any moment, rewriting reality itself in an instant? This isn't the plot of a dystopian sci-fi novel. It's the spine-chilling possibility of vacuum decay, a scenario where the very fabric of space-time could undergo a catastrophic phase transition, erasing everything we know in a flash. The trigger, a single quantum event, random and unpredictable, that tips the cosmos from a false vacuum into a true lower energy state. In that moment, the laws of physics as we understand them would cease to exist, replaced by new constants and forces that might render life, matter, even light itself unrecognizable. To grasp this doomsday mechanism, imagine the universe's current vacuum state as a marble resting on the slope of an impossibly tall mountain. It seems stable for now. But somewhere beneath it lies a deeper valley, a state of far lower energy. Quantum mechanics tells us that given enough time, the marble will eventually find its way down. It might take an eternity, or it could happen tomorrow. All it takes is a tiny nudge, a quantum fluctuation powerful enough to push the marble over the edge. When that happens, a bubble of this new vacuum would form at light speed, expanding outward like an unstoppable cosmic wildfire. Inside that bubble, atoms would disintegrate, forces would reconfigure, and the universe as we know it would vanish without a trace. The math behind this nightmare comes from a concept called false vacuum theory, which suggests our vacuum isn't the lowest possible energy state, just a local minimum, like a dip in an otherwise descending landscape. Particle accelerators have searched for clues by measuring the Higgs boson's mass, hoping to confirm whether our vacuum sits safely in the deepest valley. So far, the data is unsettlingly ambiguous. Some calculations hint we're in a precarious, metastable state, meaning we're stable until we're not. But here's where it gets stranger. This bubble of true vacuum wouldn't just destroy Earth, it would race across the cosmos at the speed of light, leaving no warning. One moment, stars twinkle as usual. The next, an invisible wall of annihilation sweeps through, rewriting the rules of existence before any signal could reach us. Scientists call this process bubble nucleation, and it's as elegant as it is horrifying. A single quantum event spawns a sphere of death that grows exponentially, consuming galaxies like a drop of ink in clear water. Is there any hope? Some theories suggest the vacuum's stability might depend on undiscovered particles or symmetries that anchor our current state. Others argue that if the universe were truly this fragile, vacuum decay would have already happened somewhere in the observable cosmos, and the absence of such an event might be a quiet reassurance. But until we know for sure, vacuum decay remains the ultimate existential gamble. A reminder that beneath the apparent solidity of reality lies a quantum roulette wheel spinning silently in the dark. The irony is poetic. The same quantum vacuum that births particles from nothing could also be the architect of total cosmic annihilation. One thing's certain, if the universe is a house of cards, we're only just beginning to understand how delicate its foundations really are. And somewhere out there, in the infinite expanse of space-time, a single quantum tremor could be all it takes to bring the whole thing crashing down. The odds of vacuum decay happening tomorrow, or even in the next trillion years, are vanishingly small. But small doesn't mean zero. Physicists crunching the numbers estimate the probability sits somewhere around 1 in 10 to the power of 100. To put that in perspective, you're more likely to spontaneously quantum tunnel through your chair right now than witness the universe unravel. Yet even these infinitesimal odds carry weight when you consider the stakes. Not just our planet or galaxy, but every star, every atom, every law of physics rewritten in an instant. The Higgs boson holds the key to this cosmic suspense. Its mass, measured at 125 gigaelectronvolts, places our vacuum in a precarious zone between stability and doom. Think of it like balancing a pencil on its tip. It might stand for an hour, a day, or a century, but eventually it will fall. The Higgs suggests our universe is that pencil, teetering in a metastable state. Not actively collapsing, but not perfectly secure either. If future colliders discover new particles or interactions that adjust this balance, we might exhale in relief. But right now, the uncertainty lingers like a shadow. What makes this gamble even stranger is the possibility that we're not the first to play it. In an infinite multiverse, countless universes could have already succumbed to vacuum decay. Picture bubbles of true vacuum bursting like cosmic soap foam across dimensions, each erasing its own version of reality. Some theories suggest these collapses might even leave faint imprints, anomalies in the cosmic microwave background, or bizarre particle behavior, hinting at neighboring universes that weren't so lucky. Yet there's a twisted comfort in the math. Even if vacuum decay started today, the bubble would take billions of years to reach us. By then, the universe's expansion may have pushed galaxies so far apart that the wavefront never arrives. Dark energy could ironically be our shield, stretching spacetime faster than doom can spread. So is our universe doomed? Maybe, but maybe stretches across timelines so vast they dwarf human imagination. The vacuum's fragility isn't a countdown, it's a mirror, reflecting how delicately the cosmos balances between existence and oblivion. And in that reflection, we find something oddly beautiful, a universe that persists not because it must, but because it can, at least for now. Imagine hurtling through space in a rocket, accelerating faster and faster until suddenly, the empty void around you starts glowing with heat. This isn't a hallucination. It's the Unravel effect, one of quantum physics' most startling predictions, the idea that motion itself can conjure particles from nothingness. According to the equations, an observer accelerating through the vacuum would detect a warm bath of radiation, as if the universe had turned up the thermostat just for them. To someone standing still, that same space remains icy and empty. The shocking implication: reality isn't just out there, it's something we participate in, shaped by how we move through the cosmos. At the heart of this phenomenon lies Einstein's equivalence principle, the same insight that birthed general relativity. It tells us acceleration and gravity are indistinguishable. If you're sealed in a windowless spaceship, you can't tell whether the force pinning you to the floor comes from rocket engines or a planet's pull. The Unravel effect takes this idea and twists it into quantum territory. Just as Hawking radiation makes black holes glow with heat due to their gravitational grip, acceleration warps the quantum vacuum in a similar way. Virtual particle pairs, normally flickering in and out of existence too quickly to notice, get stretched apart by the accelerating motion. Some are left stranded as real particles, their energy siphoned from the void itself. The result: a thermometer in your rocket would register a temperature proportional to your acceleration, a ghostly warmth born purely from your own motion. But here's where physics gets philosophical. If particles can appear or disappear based on an observer's acceleration, does that mean reality is fundamentally subjective? The equations suggest an unsettling answer. What one observer sees as empty space, another might measure as a particle-filled inferno. It's not that the vacuum changes, it's that the definition of a particle depends on who's looking. Picture two astronauts, one floating inert in space, the other firing thrusters. The first sees nothing, the second gets bathed in Unravel radiation. Both are correct, yet their experiences contradict. This duality echoes quantum mechanics' deepest puzzles, like Schrödinger's cat being both alive and dead. But unlike that thought experiment, the Unravel effect isn't hypothetical, it's a direct consequence of marrying quantum theory with relativity. Detecting Unravel radiation directly is nearly impossible with current technology. To feel even a 1-degree temperature rise, you'd need to accelerate at a quadrillion times Earth's gravity, far beyond any human-made machine. Yet the effect's fingerprints appear in unexpected places. Some theorists argue it plays a role in the thermal noise plaguing ultra-sensitive particle detectors, like those hunting dark matter. Others suggest it could explain why rapidly moving electrons in particle accelerators sometimes behave as if they're swimming through a resistive medium, as though space itself pushes back. Even wilder are proposals linking Unravel radiation to the early universe's expansion, where colossal accelerations might have forged particles from the vacuum on cosmic scales. The Unravel effect ultimately forces us to confront a humbling truth. The universe has no single objective stage. Like a cosmic chameleon, its appearance shifts depending on how we interact with it. Acceleration doesn't just change our speed, it rewires our entire perception of reality, revealing particles where none existed before. Whether this means reality is observer-dependent or simply that our language of particles is too crude to capture deeper truths remains an open wound in physics. But one thing's certain: the vacuum is far more sensitive to our movements than we ever imagined, and every acceleration, no matter how slight, tells a different story about the nature of existence. Zoom in far enough, past atoms, past quarks, past anything we've ever measured, and spacetime itself begins to boil. At scales a billion trillion times smaller than an atom, the smooth, predictable fabric of the universe dissolves into a chaotic froth known as quantum foam. Here, the very concepts of here and now lose meaning as spacetime churns with violent fluctuations. Tiny wormholes pinch open and shut like bubbles in a carbonated drink. Microscopic black holes erupt into existence only to evaporate moments later. It's as if the cosmos is built on a foundation of fizz, where geometry itself is nothing more than an average of infinite frenzied twists and folds. This dizzying vision comes from merging quantum mechanics with general relativity, two theories that usually refuse to play nice. Einstein's equations describe spacetime as a smooth, bendable sheet. Quantum theory insists everything, even space and time, must have some graininess at the smallest scales. Quantum foam is where these ideas collide. Imagine trying to measure the surface of a pond with a ruler made of gelatin. The act of measurement distorts the very thing you're studying. At Planck length around 10 to the power of minus 35 meters, spacetime becomes so jittery that pinpointing positions or durations becomes impossible. The vacuum isn't just full of virtual particles, it's a writhing, topological storm where the stage itself is in constant upheaval. What does this mean for reality? For starters, it suggests that the orderly universe we experience is an illusion, a statistical averaging of countless violent fluctuations too small and fast to perceive. Think of it like watching a movie projected on a screen. From your seat, the images appear smooth, but up close, you'd see the individual pixels flickering on and off. Quantum foam implies spacetime has pixels too, and they're anything but stable. Wormholes in this foam could theoretically connect distant points instantaneously, though most are too tiny and fleeting to traverse. Black holes smaller than protons might form and vanish, their brief lives leaking Hawking radiation into the void. The real headache comes when physicists try to build a theory of quantum gravity, a framework to unify the large and small. Quantum foam defies both relativity's smooth spacetime and quantum field theory's orderly particles. Loop quantum gravity, one leading candidate, suggests spacetime is woven from finite loops that prevent infinite collapse. String theory proposes everything, including space, is made of vibrating strings, but neither fully explains the foam's frenzy. Some models even hint that at these scales, cause and effect might unravel, with events happening in no fixed order. Perhaps the wildest implication is that quantum foam could make time travel inevitable, not in the sci-fi sense, but as a fundamental feature of microscopic physics. If wormholes constantly form at Planck scales, then technically, every second, particles are hopping backward and forward in time, their histories braiding through the foam's chaos. Of course, scaling this up to human-sized time machines is another story. The energy required would dwarf anything in our universe, yet for all its strangeness, quantum foam might hold the key to the cosmos' deepest secrets. If we could probe these scales and no existing technology comes close, we might witness the primordial forge where spacetime itself is hammered into existence. Until then, the foam remains a tantalizing ghost in our equations, a reminder that reality, when examined too closely, dissolves into pure, beautiful madness. Einstein called it spooky action at a distance, a phrase dripping with skepticism about quantum mechanics' strangest prediction. Yet today, the EPR paradox isn't just real, it's the backbone of quantum teleportation, and the quantum vacuum is the silent conductor making it all possible. Picture two entangled particles born from the same quantum event, then flung to opposite ends of the galaxy. Measure one, and its twin instantly snaps into a corresponding state, as if space and time between them don't exist. This isn't magic, it's the vacuum's hidden wiring at work, a web of non-locality where information bypasses the speed of light by riding the quantum foam itself. The original thought experiment, dreamed up by Einstein, Podolsky, and Rosen in 1935, was meant to expose quantum theory's absurdity. How could particles coordinate faster than light without breaking relativity? The answer lies in the vacuum's role as the universe's ultimate switchboard. When particles entangle, their quantum states become a shared property of the system, woven into the vacuum's fluctuating fields. Measuring one doesn't send a signal to the other. Instead, it updates the underlying quantum field connecting them, like two hands moving in sync because they're part of the same puppet. The vacuum doesn't transmit information, it already is the information, a holographic medium where distance is an illusion. this eerie connection isn't theoretical. Labs have teleported quantum states across dozens of miles using entangled photons, with the vacuum acting as the invisible bridge. In one famous experiment, scientists on the Canary Islands beamed entangled particles between two telescopes separated by 144 kilometers. When one photon's polarization was measured, its partner, despite being halfway to the edge of space, mirrored the change instantaneously. The kicker: this teleportation doesn't move matter or energy. It transfers quantum information etched into the vacuum's ephemeral fluctuations. But here's the twist that unsettled Einstein. This process doesn't violate relativity because no usable data is actually exchanged faster than light. You can't control the outcome of a measurement, so while the correlation is instantaneous, it's useless for sending messages. It's like sharing a pair of quantum dice. Rolling one in Tokyo automatically determines the other's result in Paris, but neither of you chose what numbers appeared. The vacuum enables this cosmic conspiracy without breaking causality, a loophole so clever it redefines our notion of connection. What's even wilder is how this plays out in the vacuum's structure. Entanglement isn't limited to particle pairs, it's a fractal web linking everything that's ever interacted. Some theories suggest the entire universe was once entangled in a hot, dense state, and remnants of those quantum handshakes still linger in the vacuum today. If true, then every interaction, from atoms bonding to neurons firing, might trace back to this primordial network, with the vacuum serving as the universe's original social platform. The implications ripple from philosophy to technology. Quantum computers leverage entanglement to perform calculations impossible for classical machines, while future quantum networks might use the vacuum's non-locality to build unhackable communication grids. Yet beneath these marvels lurks a deeper mystery. Is the vacuum the true substrate of reality, a canvas where particles are mere brushstrokes? Einstein's spookiness might have been a warning, not about quantum theory's flaws, but about the vacuum's power to stitch the cosmos together in ways we're only beginning to fathom. Picture an electron orbiting a hydrogen atom, but instead of moving smoothly like a planet around the sun, it's constantly jittering, knocked ever so slightly off course by unseen quantum tremors. This minuscule wobble, barely detectable even with the most precise instruments, is the Lamb shift, a whisper from the quantum vacuum that forever changed our understanding of atoms. In 1947, physicist Willis Lamb turned spectroscopy into a detective tool, uncovering an anomaly in hydrogen's energy levels that classical physics couldn't explain. The gap between two specific electron orbits was slightly wider than theorists predicted, as if an invisible hand were gently pushing them apart. That hand turned out to be the restless quantum vacuum itself, its seething energy subtly reshaping the atom from within. Here's how it works. Even in empty space, electromagnetic fields never truly zero out. They're alive with vacuum fluctuations, virtual photons popping in and out of existence. When an electron orbits a proton, these phantom photons briefly alter its electromagnetic environment, like a calm lake disturbed by countless tiny raindrops. Some virtual photons push the electron slightly away from the nucleus, while others pull it closer. On average, this quantum turbulence reshuffles the electron's energy states, creating the Lamb shift signature split. It's as if the vacuum itself is a subtle sculptor, chiseling away at atomic structure with ethereal tools. Lamb's experiment was a masterclass in precision. Using microwave beams to probe hydrogen atoms, he detected energy differences smaller than 1 part in a million, akin to measuring the thickness of a hair from 10 miles away. His results weren't just a curiosity, they were a death blow to the old quantum theory of Dirac, which had treated the vacuum as perfectly still. The shift demanded a new framework, quantum electrodynamics, or QED, where particles and fields danced together through a sea of virtual interactions. Theorists like Feynman, Schwinger, and Tominaga rose to the challenge, crafting equations that accounted for the vacuum's tireless activity. Their calculations matched Lamb's data with stunning accuracy, confirming QD as the most precise theory in all of science. The implications ripple far beyond atomic physics. The Lamb shift proved that empty space isn't a passive backdrop, it's an active participant in shaping matter. Every atom in your body carries this quantum fingerprint, its electrons nudged by vacuum fluctuations since the dawn of time. Modern atomic clocks, so accurate they'd lose less than a second over 15 billion years, must account for these subtle shifts. Even the search for new physics relies on Lamb's legacy. Discrepancies in predicted versus measured shifts could hint at undiscovered particles or forces tweaking the vacuum's behavior. Perhaps most profoundly, the Lamb shift revealed that reality is never pristine. The quantum world is a constant negotiation between particles and the seething void they inhabit, where even the simplest atom bears scars from its endless duel with nothingness. It's a reminder that the universe doesn't play by neat, classical rules. It thrives in the messy, vibrant interplay between what's there and what might be. The vacuum isn't just fragile to acceleration or motion, it can be torn apart by raw electric force, a phenomenon so dramatic it bends the rules of existence. This is the Schwinger effect, named after physicist Julian Schwinger, who predicted that an electric field strong enough could literally rip pairs of particles and antiparticles from the void itself. Picture the vacuum as a taut fabric stretched to its limit. Then, with a sudden surge of energy, it frays at the seams, unraveling into tangible matter. Under extreme conditions, empty space isn't empty at all. It's a reservoir of potential particles waiting for the right trigger to burst forth. How does this quantum magic trick work? Normally, virtual particle-antiparticle pairs flicker in and out of existence too quickly to detect. But an electric field of sufficient strength can yank them apart before they have a chance to annihilate each other. It's like pulling two magnets apart. Once separated beyond a critical distance, they can't snap back together. In this case, the energy required to tear them apart comes from the electric field itself, which acts like a cosmic crowbar prying reality open. The math behind this is staggering. You'd need fields around 1,000,000 billion volts per meter, far beyond anything found naturally on Earth. Yet in the depths of space, nature has no trouble conjuring such extremes. Enter pulsars, the universe's ultimate particle accelerators. These rapidly spinning neutron stars boast magnetic fields trillions of times stronger than Earth's, with electric potentials so intense they turn the surrounding vacuum into a particle factory. Near a pulsar's magnetic poles, the Schwinger effect is thought to churn out electron-positron pairs in vast cascades, fueling the star's deadly radiation jets. These particles don't just appear, they're launched at nearly light speed, creating the lighthouse-like beams we detect as pulsar beats. It's one of the few places in the cosmos where quantum field theory manifests on a macroscopic scale, proving that the vacuum's secrets aren't just lab curiosities, they sculpt the most violent objects in the sky. But what about recreating this phenomenon here on Earth? For decades, the Schwinger effect was purely theoretical. No human-made electric field could come close to the required intensity. That's starting to change. Advances in laser technology, like the upcoming Exawatt Center for Extreme Light Studies, XCELS, aim to concentrate pulses of light into unimaginably tiny volumes, creating transient fields that might finally reach the Schwinger threshold. Imagine firing two ultra-powerful lasers at a single point in a vacuum chamber for a fraction of a nanosecond. The intersecting beams could distort space-time enough to wring particles from nothingness. If successful, it would be the ultimate alchemy, turning light directly into matter, no stars or supernova required. Yet even if we succeed, the implications raise thorny questions. If we can generate matter from empty space, does that mean energy and particles are somehow encoded into the fabric of reality itself? Could advanced civilizations harness this effect to power their machines, or would quantum back reaction, the newly created particles weakening the field that birthed them, make it a fleeting phenomenon? And most hauntingly, if the vacuum can be broken so easily under extreme conditions, what does that say about its stability across the cosmos? The Schwinger effect isn't just a laboratory goal, it's a window into the profound link between the quantum world and the forces that shape our universe, proving once again that nothingness is the most deceptive concept of all. Imagine the vacuum as a cosmic hall of mirrors, where every electron in the universe is surrounded by an entourage of ghostly reflections. This isn't just poetic imagery, it's vacuum polarization, a bizarre quantum phenomenon where virtual particle-antiparticle pairs swarm around charged particles like bees around a hive, subtly warping the very forces that bind the cosmos. At its heart lies a mind-bending twist. The empty space between charges isn't neutral. It's a dynamic sea of fleeting dipoles aligning themselves to soften or amplify electromagnetic fields in ways that defy classical intuition. Here's how this quantum sleight of hand works. When an electron sits in the vacuum, it constantly emits and reabsorbs virtual photons, the carriers of the electromagnetic force. But those photons can briefly morph into virtual electron-positron pairs, which immediately annihilate back into photons. This fleeting creation isn't just background noise, it transforms the vacuum into a dielectric medium, like the insulating material between capacitor plates. The virtual positrons are drawn toward the real electron, while the virtual electrons are repelled, creating a microscopic screening effect. From afar, the electron's charge appears slightly weaker than its bare value because these polarized virtual pairs act like a cloud of quantum bodyguards, intercepting and redirecting electromagnetic interactions. This screening effect isn't theoretical gymnastics, it's been measured with breathtaking precision. Take the muon, the electron's heavier, unstable cousin. Its magnetic moment, a measure of how it interacts with magnetic fields, should be exactly 2 according to Dirac's equation. But the vacuum's polarization adds tiny corrections, like a cosmic spice that subtly alters the flavor of physics. Virtual particles of all types, not just electrons and positrons, but also heavier quarks and even hypothetical particles, contribute to this quantum froth. When physicists at Brookhaven National Lab and later at Fermilab trapped muons in magnetic storage rings, they found the muon's magnetism ever so slightly stronger than predicted. This anomalous magnetic moment matches QED's calculations of vacuum polarization to within 1 part in a billion, a triumph of theory and experiment dancing in perfect sync. Yet there's a tantalizing wrinkle. Recent measurements show a persistent discrepancy between the muon's behavior and the standard model's predictions, about 2.5 parts per billion. It's a tiny gap, but in the razor-sharp world of particle physics, it could be the first crack revealing entirely new physics. Some theorists speculate that undiscovered particles, perhaps those predicted by supersymmetry, might be lurking in the vacuum's polarized shadows, tweaking the muon's properties in ways we haven't yet accounted for. Others caution that the anomaly might stem from underestimated hadronic effects. Either way, vacuum polarization isn't just a quantum quirk, it's a forensic tool magnifying hints of deeper layers in reality's fabric. What's truly astonishing is how this process scales. In extreme environments like neutron star crusts or heavy ion colliders, where densities and temperatures approach primordial extremes, vacuum polarization can become so intense it alters the very nature of matter. Protons and neutrons might dissolve into quark-gluon plasma as the vacuum's screening effects overwhelm the strong nuclear force. Even light propagating through these polarized voids could slow or bend in unexpected ways, as if space itself acquired refractive properties. The vacuum, it turns out, is the ultimate chameleon, its behavior shifting dramatically based on the energy and scales we probe. So the next time you hear that opposites attract, remember, the quantum vacuum takes that idea to surreal extremes. For every charge in the universe, there's an invisible entourage of virtual opposites, twisting the rules of attraction and repulsion in ways we're still deciphering. And hidden within those subtle twists might just be the clues to everything we don't yet understand about the forces that shape reality. The numbers just don't add up, and we're not talking about a small accounting error here. When physicists tally up all the quantum fluctuations simmering in the vacuum, the total energy should be colossal enough to curl space-time into a singularity. But when astronomers measure the universe's actual curvature, they find something far weaker, a hum so faint it's like comparing the roar of a supernova to a single photon's whisper. This staggering mismatch, known as the vacuum catastrophe, isn't just a minor puzzle, it's the most embarrassing discrepancy in all of science, revealing a rift between quantum theory and cosmology so wide it threatens to undermine our understanding of reality itself. Dig into the math and the absurdity becomes clear. Every quantum field electromagnetic electron quark contributes to the vacuum's energy density. Sum them up, and you'd expect space to weigh in at around 10 to the power of 112 joules per cubic meter. Yet observations of cosmic expansion peg dark energy's density at a mere 10 to the power of -9. That's a difference of 120 orders of magnitude, a number so vast it dwarfs the total atoms in the observable universe. It's as if you calculated the weight of Mount Everest but stepped on a scale that registered the mass of a single snowflake. So where did we go wrong? One camp argues the catastrophe exposes a blind spot in quantum field theory. Perhaps the vacuum's energy isn't additive, or unknown symmetries cancel out most contributions. Supersymmetry, a popular but still unproven framework, posits every particle has a superpartner whose vacuum fluctuations neatly offset their own. But even if supersymmetry exists, current experiments suggest it can't bridge the full gap. Others propose radical fixes like variable vacuum energy that leaks into extra dimensions or gets diluted by cosmic inflation's stretching of spacetime. Then there's the multiverse gambit. If our universe is one bubble among infinite others, each with randomly determined vacuum energies, we might simply reside in a rare oasis where the value is survivably low. This anthropic reasoning skirts the math entirely instead of explaining the mismatch. It argues we couldn't exist in a universe where the numbers made sense. Critics dismiss this as a cop-out, but supporters counter that dismissing it might be like a fish denying the existence of water because it's never seen dry land. The vacuum catastrophe isn't just academic, it's a ticking time bomb for theoretical physics. If no solution emerges, we may need to tear up quantum mechanics, general relativity, or both. Yet within this crisis lies an exhilarating possibility. The crack we're staring into might be the very portal to the next great revolution in science. After all, the universe loves irony. Its greatest secrets often hide in plain sight, disguised as its most glaring failures. Black holes aren't just cosmic vacuum cleaners. They're also the universe's most surprising librarians, meticulously recording information in a way that defies everything we thought we knew about entropy. In the 1970s, Jacob Bekenstein and Stephen Hawking made a startling discovery. A black hole's event horizon isn't just a point of no return. It's a ledger, its surface area encoding the total entropy of everything that ever fell inside. This revelation, now called Bekenstein-Hawking entropy, didn't just redefine black holes. It exposed a profound link between gravity, quantum mechanics, and the hidden structure of the vacuum itself. At first glance, the idea seems absurd. Entropy, the measure of disorder in a system, usually depends on volume. More space means more ways particles can arrange themselves. But black holes flip this logic upside down. Their entropy scales with the area of their event horizon, not the volume within. A black hole with twice the radius doesn't have 8 times the entropy as volume would dictate, it has just 4 times. This bizarre property hints that the vacuum might not store information the way we imagine. Instead of being scribbled throughout three-dimensional space, data could be painted on a two-dimensional surface like a cosmic hologram, with the third dimension emerging as an illusion. The holographic principle, born from this insight, suggests that the vacuum's true microstates, the fundamental configurations that give rise to entropy, aren't scattered through space like leaves in a forest. They're etched onto its boundaries like a movie projected from the edges of reality onto the screen we experience. Picture a room where every object, every interaction, is actually a pattern of pixels on the walls, creating the appearance of depth. In this view, the vacuum's infinite complexity might be simpler than we thought, compressed into a lower dimensional code that our three-dimensional brains struggle to decode. But how does this connect to the quantum vacuum? Imagine virtual particle pairs popping into existence near a black hole's event horizon. Normally, they'd annihilate in a flash. But if one falls in while the other escapes as Hawking radiation, the black hole loses mass and its horizon shrinks. Here's the twist: the escaping particle carries away information about the black hole's state, subtly altering its surface area in a way that preserves entropy. This delicate dance implies that the vacuum's fluctuations aren't random noise, they're part of an intricate data preservation system, where every quantum event updates the cosmic ledger. The implications ripple far beyond black holes. If the holographic principle holds, the vacuum we perceive might be a projection, a shadow cast by processes happening on some distant, abstract surface we can't yet perceive. String theorists posit this boundary could reside in a higher dimensional space, while others suggest it's woven into the fabric of space-time itself. Either way, the idea forces us to confront a humbling possibility. The vacuum's true nature might be written in a language of geometry we're only beginning to decipher, where information, entropy, and gravity are threads in a tapestry far stranger than we ever dreamed. And that raises one last electrifying question. If the vacuum is a hologram, what or who is holding the projector? Paul Dirac was staring at an equation that seemed to predict the impossible electrons with negative energy. It was 1928, and his groundbreaking work unifying quantum mechanics with special relativity had birthed a monster. The math insisted that for every ordinary electron, there should be a mirror version lurking in negative energy states, like shadows cast below the floor of reality. Rather than dismiss this as mathematical noise, Dirac dared to take it seriously, proposing an audacious vision. The entire vacuum might be a vast, invisible ocean, the Dirac Sea, where every possible negative energy state was already occupied. What we perceive as empty space, he argued, is actually a cosmic plenum, brimming with particles we simply can't detect because they're buried beneath an impenetrable quantum surface. This wasn't just poetic imagery, it was a desperate fix to prevent positive energy electrons from cascading endlessly into these negative states, which would have made atoms catastrophically unstable. Dirac's solution: the sea is already full. Like water in a submerged glass, electrons can't fall lower because there's no room left. But just as lifting water creates a bubble, exciting the vacuum could eject a negative energy electron, leaving behind a hole in the sea. That hole, Dirac realized, would behave exactly like a particle with opposite charge, an anti-electron, or positron. 3 years later, Carl Anderson spotted these very particles in cosmic rays, cementing Dirac's reputation as a visionary and giving birth to antimatter physics. Yet the Dirac Sea was always a strained metaphor. It required accepting that the vacuum contained an infinite number of particles, all invisibly packed together, a notion that made even Dirac uneasy. When quantum field theory emerged, it offered a cleaner explanation. Particles and antiparticles are simply excitations of underlying quantum fields, with no need for an infinite ocean. Modern physics treats the positron not as a hole in some subterranean electron sea, but as a legitimate particle in its own right, popping into existence when energy is pumped into the electron field. The Dirac sea, in this view, is like Newton's luminiferous ether, a useful stepping stone that was ultimately replaced by more elegant machinery. But here's the twist: Dirac's intuition still echoes through modern physics in surprising ways. The vacuum of quantum field theory isn't truly empty. It's seething with potential particles, much like the churning sea he envisioned. And when physicists probe high-energy collisions, they still describe particle creation in language that would have made Dirac smile. Pair production evokes his idea of lifting electrons from the depths, while annihilation mirrors holes and particles recombining. Even the concept of Fermi surfaces in condensed matter, where electrons behave like a liquid filling up energy states, owes a debt to Dirac's original metaphor. Perhaps the sea's greatest legacy is how it reshaped our intuition about nothingness. Before Dirac, the vacuum was a static stage. After him, it became a dynamic medium, one that could be stirred, stressed, and even punctured. Modern theories like the Higgs mechanism, where particles acquire mass by interacting with a pervasive field, carry faint whispers of Dirac's vision. And in the speculative world of quantum gravity, some models still invoke sea-like structures to explain dark energy or spacetime's granularity. The Dirac sea may have drained away as literal truth, but its ripples continue to influence how we grapple with the universe's deepest mysteries, a reminder that even wrong ideas can illuminate the path to revelation. Even the vacuum has a voice, a soft hiss of quantum noise that sets the ultimate limit on how precisely we can measure the universe. But what if we could twist that noise, reshaping it like putty to quiet certain fluctuations while amplifying others? This is the essence of vacuum squeezing, a quantum trick so counterintuitive it feels like cheating reality itself. By manipulating the vacuum's inherent jitter, scientists can effectively silence its whispers in one dimension to gain supernatural clarity in another. It's as if the universe handed us a blurry photograph, and we discovered a way to sharpen just the details we need while letting the rest fade into static. The magic lies in Heisenberg's uncertainty principle, which dictates that certain pairs of quantum properties, like a particle's position and momentum, can never both be pinned down with perfect precision. The vacuum's fluctuations embody this trade-off, with equal uncertainty distributed between these conjugate variables. Squeezing tilts the balance. Using nonlinear optics or atomic interactions, physicists compress the uncertainty in one variable below the standard quantum limit, while accepting increased noise in its partner. Picture a balloon. Squeezing one side makes the opposite side bulge. Similarly, by flattening the vacuum's noise in, say, the amplitude of light waves, we gain ultra-precise phase measurements at the cost of extra amplitude fuzziness we don't care about. This technique isn't just lab table wizardry, it's revolutionizing how we listen to the cosmos. Gravitational wave observatories like LIGO employ squeezed light to detect spacetime ripples from colliding black holes billions of light-years away. Without squeezing, the vacuum's quantum noise would drown out these faint whispers. By injecting light squeezed in the right variable, LIGO achieves sensitivities that let it measure displacements smaller than 1,000th the width of a proton. It's akin to detecting a grain of sand dropped on the moon from Earth, a feat that earned the 2017 Nobel Prize and opened a new window onto the violent universe. But the implications stretch far beyond astronomy. Quantum squeezing could supercharge future technologies, from unhackable quantum communication networks to brain scanners with unprecedented resolution. Imagine MRI machines that peer into individual neurons, or atomic clocks so precise they'd lose less than a second over the age of the universe. Some labs are even exploring squeezed states in mechanical oscillators, microscopic drumheads chilled to near absolute zero, where quantum noise reduction might one day enable sensors capable of weighing individual viruses or mapping protein structures atom by atom. Yet squeezing's greatest promise might be philosophical. By bending the vacuum's rules without breaking them, we're learning that nature's limits aren't always where we thought. The same quantum fuzz that once seemed an insurmountable barrier is now a malleable resource waiting to be sculpted. It's a reminder that sometimes progress doesn't mean pushing harder against the universe's constraints, but learning to dance within them, reshaping the noise into a symphony of precision. For decades, dark matter has been the universe's most frustrating jigsaw piece, an invisible force sculpting galaxies, bending light, and outweighing normal matter 5-1, yet stubbornly refusing to reveal its true nature. But what if we've been searching in the wrong places? Instead of hunting for elusive particles, some theorists suggest the answer might be hiding in plain sight, woven into the quantum vacuum itself. Imagine a hidden layer of reality where the vacuum isn't just empty space, but a dynamic medium teeming with undiscovered fields and particles so weakly interacting they've slipped past every detector built so far. One leading candidate springs from an attempt to solve a completely unrelated puzzle: why the strong nuclear force obeys something called charge parity symmetry, or CP, with near-perfect precision. This symmetry implies that quarks and their mirror image counterparts behave identically, which shouldn't happen according to most theories. To fix this, physicist Roberto Pexi and Helen Quinn proposed a new quantum field that permeates the vacuum, one whose value naturally adjusts to preserve CP symmetry. The catch: this field would ripple through spacetime as ultra-light, ghostly particles called actions, born from the vacuum's subtle oscillations. Actions are bizarre even by quantum standards. They'd be billions of times lighter than electrons, barely interacting with normal matter, yet collectively, they could form a cosmic fog dense enough to explain dark matter's gravitational grip. Picture the vacuum as a vast piano, with actions as its faintest notes, vibrations so soft they're drowned out by the universe's noise, but whose combined hum shapes the cosmos. Unlike bulky, weakly interacting massive particles, WIMP, actions wouldn't need exotic detectors to spot them. When passing through powerful magnetic fields, theory predicts they'd occasionally convert into microwave photons, like shadows stepping into the light. Experiments like ADMX and Haystack are hunting this telltale signal using superconducting resonators chilled to near absolute zero, listening for the vacuum's whisper in the electromagnetic static. But actions aren't the only vacuum-born dark matter suspects. Some models suggest entire families of ultralight particles, dubbed fuzzy dark matter, could emerge from quantum fields we've yet to discover. These wouldn't behave like discrete particles at all, but as wave-like disturbances in the vacuum, their wavelengths stretching across light years. Galaxies embedded in such a field would act like boats on a pond, with ripples subtly altering their rotation in ways that match observed dark matter effects. Other theories propose hidden sectors, parallel quantum fields interacting with ours only through gravity, their vacuum fluctuations imprinting invisible mass on the cosmos. The beauty of these ideas is how they flip the dark matter problem on its head. Instead of searching for missing pieces, we might be staring at the puzzle's fabric, realizing too late that the gaps aren't empty, but filled with structures too subtle to see. And if the vacuum holds the key, it would mean dark matter isn't some foreign invader. It's the hidden rhythm of reality itself, a bassline to the universe's song that we're only just learning to hear. What if time isn't a fundamental part of the universe, just an illusion that emerges from something deeper? That's the radical proposition buried in the Wheeler-DeWitt equation, a controversial formula so audacious it erases time from the fabric of reality. Conceived in the 1960s by physicists John Wheeler and Bryce DeWitt, this equation attempts to unite quantum mechanics with general relativity, but in doing so, it produces a staggering side effect: a universe frozen in an eternal present where the concept of now dissolves into quantum static. At its core, the equation describes the quantum state of the entire cosmos, treating spacetime as a single, unchanging entity, like a cosmic block of ice rather than a flowing river. Unlike Schrödinger's equation, which tracks how quantum systems evolve over time, the Wheeler-DeWitt equation lacks any time parameter whatsoever. It's as if the universe's birth certificate arrived with the date and hour mysteriously blank. This problem of time, as physicists call it, suggests that what we experience as the passage of moments might be a trick of the quantum vacuum's underlying structure, a holographic projection emerging from timeless, fluctuating foam. Think of it like watching a movie. On screen, characters move through time, but the film strip itself is static, every frame already fixed in place. The Wheeler-DeWitt equation hints that reality works the same way. The quantum vacuum holds all possible frames simultaneously, and our perception of change is just a mental stitching together of these frozen instants. This idea finds eerie support in loop quantum gravity, where spacetime isn't smooth but granular, a network of interconnected atoms of space whose relationships create the illusion of continuity. Near the Big Bang, these grains would have been so jumbled that time as we know it couldn't exist, raising the spine-tingling possibility that time itself was born from the vacuum's quantum chaos. But if time isn't fundamental, where does our vivid experience of it come from? Some theorists argue it emerges from entanglement, the quantum links between particles creating a directionality we perceive as time's arrow. Others propose it's a thermodynamic mirage, with increasing entropy painting the illusion of past and future onto a timeless canvas, the most radical interpretation. That time is a collective hallucination, a story the universe tells itself to make sense of the vacuum's infinite possibilities. The implications ripple through cosmology. If the Wheeler-DeWitt equation holds, the Big Bang wasn't an explosion in time. It was the moment time crystallized from timelessness, like frost forming on a window. This could explain why quantum gravity calculations avoid the singularity problem. Without time, there's no before the Big Bang to worry about. It also casts black holes in a new light. Their event horizons might not just trap matter, but fragments of time itself, leaving internal clocks frozen from our perspective while continuing normally within. Yet the equation remains fiercely debated. Critics argue it's a mathematical artifact, missing key ingredients like quantum decoherence. Others note its time-free universe clashes violently with our experience, a disconnect jokingly called the tragedy of the Wheeler-DeWitt equation. But its central insight lingers. The vacuum might not just host particles and forces, but the very stage of reality itself. And if time is indeed an emergent property, then every tick of the clock is a quantum magic trick, a whisper from the void, reminding us that nothing, not even time, is what it seems. In the crushing magnetic embrace of a neutron star, even the vacuum itself can't stay impartial. It takes sides with light, bending one polarization differently than another in a quantum feat so bizarre it shouldn't exist. This is vacuum birefringence, a phenomenon where empty space, under extreme conditions, behaves like a cosmic crystal, splitting light into two distinct paths as if space itself developed an optical axis. Normally, birefringence is the domain of materials like calcite or quartz, where atomic structures force light waves to travel at different speeds depending on their orientation. But in the presence of magnetic fields trillions of times stronger than Earth's, the quantum vacuum reveals its hidden graininess, warping the very rules of electromagnetism. Here's the quantum sleight of hand at work. The vacuum isn't truly empty, it's a frothing sea of virtual electron-positron pairs that momentarily pop into existence. Under normal circumstances, these fleeting particles cancel each other out perfectly, but introduce a magnetic field strong enough and everything changes. The field polarizes these virtual charges, aligning them like microscopic compass needles. Light passing through this magnetized vacuum now interacts differently depending on its polarization. Photons oscillating parallel to the magnetic field feel a stiffer medium, slowing them slightly, while perpendicular photons glide through unaffected. The result, a splitting of light into two beams like a prism for the quantum void. Astronomers might have caught this effect in action near RxJ 1856, 3754, a neutron star 300 light-years away. When the European Space Agency's XMM-Newton telescope analyzed its X-ray emissions, they detected a faint but telltale signature, an excess of one polarization over another that couldn't be explained by scattering or interstellar dust. The likely culprit, vacuum birefringence sculpting the star's radiation as it traversed the hellish magnetic environment just miles above the surface. It's as if the vacuum itself became a lens, imprinting its quantum fingerprint onto light that had traveled for centuries to reach us. What makes this discovery so revolutionary is how it blurs the line between nothing and something. The vacuum isn't just hosting particles, it's acquiring properties we once thought exclusive to matter. In neutron star magnetospheres, this effect could even redirect radiation jets, like a cosmic traffic cop steering light based on its polarization. Some theories suggest vacuum birefringence might also occur in the relics of the early universe primordial magnetic fields left over from the Big Bang, subtly twisting the polarization of the cosmic microwave background. If so, the vacuum's crystal-like behavior could be a hidden architect of the cosmos, bending light on scales we're only beginning to perceive, yet the implications go deeper than astronomy. Quantum field theory predicts that at energies high enough, perhaps achievable in future colliders, even lab-generated magnetic fields could induce detectable birefringence. Imagine probing the vacuum structure not with telescopes, but by firing polarized lasers through superconducting magnets strong enough to make space itself flinch. Such experiments could test whether other predicted vacuum effects like nonlinearities where photons interact with themselves might also lurk in nature's playbook. The neutron star's whispered confession changes everything. If the vacuum can act as a crystal under extreme conditions, what other material-like properties lie dormant in the void? Could there be circumstances where it becomes a superconductor, a fluid, or even a cosmic amplifier? The answers might rewrite not just our maps of stellar neighborhoods, but the very definition of empty space, proving once again that the quantum vacuum is the universe's most versatile illusionist, capable of conjuring substance from the thinnest of air. The quantum foam doesn't just churn with microscopic black holes and virtual particles, it might also be threaded with tunnels, tiny wormholes stitching the fabric of spacetime into a hidden labyrinth. These aren't the cosmic shortcuts of sci-fi lore, but fleeting Planck-scale structures predicted by Einstein's equations, where spacetime pinches into a bridge before snapping shut faster than causality can traverse it. In this froth of quantum gravity, wormholes could blink in and out of existence like soap bubbles in a cosmic sink, their mouths held open for mere fractions of a second by the vacuum's violent fluctuations. Yet some theories suggest these ephemeral portals might not be doomed to collapse. If we could lace them with exotic matter or negative vacuum energy, they might just stay open long enough to whisper secrets about the universe's deepest architecture. Exotic matter sounds like something from a physicist's wish list, but it's a genuine theoretical possibility, a substance with negative energy density that could prop a wormhole's throat open against its own gravitational self-crushing. The quantum vacuum, strangely enough, might be the ultimate supplier. Under certain conditions, vacuum fluctuations can produce regions of negative energy, as demonstrated by the Casimir effect's attractive force between plates. String theory takes this further with the ER=EPR conjecture, a radical proposal that wormholes Einstein-Rosen bridges, or are fundamentally linked to quantum entanglement, Einstein-Podolsky-Rosen pairs, or EPR. In this view, every pair of entangled particles might be connected by a microscopic wormhole, their spooky action at a distance literally threaded through spacetime's hidden plumbing. Stabilizing these structures, however, demands energy densities that defy intuition. One hypothetical candidate is phantom energy, a form of dark energy so extreme it could warp the vacuum into a self-reinforcing geometry. Picture a wormhole's throat lined with this exotic vacuum, its repulsive gravity pushing outward just enough to counteract the tunnel's instinct to snap shut. The math allows for it, but the engineering is another story. Harnessing such energies would require manipulating spacetime at scales a billion times smaller than an atom, a feat beyond any foreseeable technology. Yet nature might already be doing it. Some models suggest the early universe's inflationary expansion could have stretched quantum wormholes into macroscopic structures, weaving them into the cosmos's infancy like scars in cooling glass. Others speculate that black hole singularities might birth new wormholes, their infinite curvature puncturing spacetime into pathways we can't yet map. Even if we never traverse them, their theoretical existence forces us to grapple with a startling idea. The vacuum's chaos might not just be noise, it could be the substrate of a hidden connectivity, a quantum subway system running beneath the streets of the observable universe. The deeper we probe, the more the vacuum resembles less an empty stage and more an active participant in reality's grand design. Wormholes, entanglement, dark energy, these might not be separate phenomena, but facets of a single, deeper truth written in the quantum foam's cryptic script. And if the ER equals EPR conjecture holds, then every time particles entangle, somewhere in the Planck scale frenzy, a wormhole flickers. The universe, it seems, has been threading the needle between space and correlation all along. We're just beginning to see the stitches. The universe has a glaring imbalance, one that shouldn't exist if the laws of physics played fair. For every billion particles of antimatter annihilated in the Big Bang's aftermath, a single matter particle survived to form everything we see around us. This cosmic favoritism, this one in a billion asymmetry, defies every expectation of symmetry in nature. And the key to unraveling this mystery might lie in the quantum vacuum's hidden lopsidedness, a phenomenon first outlined by Soviet physicist Andrei Sakharov in 1967. His three revolutionary conditions, CP violation, baryon number violation, and a departure from thermal equilibrium, paint a picture of a vacuum that didn't just witness the universe's matter bias but actively engineered it. At the heart of Sakharov's framework is the idea that the vacuum isn't a passive beast, and it's a dynamic medium capable of tipping the scales. CP violation, the first condition, refers to a tiny but crucial crack in nature's mirror. Normally, swapping particles with their antiparticles, charge conjugation, or C, and flipping left with right parity, or P, should leave physics unchanged. But certain quantum processes like those seen in kaon and B-meson decays reveal a slight preference for matter over antimatter. This asymmetry, measured at just 1 part in a billion, suggests the vacuum itself might have handed down a verdict favoring quarks over antiquarks in the universe's first moments. The second condition, baryon number violation, demands a mechanism to actually produce this imbalance. In our everyday world, baryons like protons and neutrons are conserved. Matter doesn't just materialize from nothing. But Sakharov realized that in the extreme heat of the early universe, the vacuum could have hosted processes that temporarily suspended this rule. Grand unified theories predict heavy particles like X-bosons, which could decay asymmetrically thanks to CP violation, producing slightly more quarks than antiquarks. As the universe cooled, these excess quarks would become locked into protons and neutrons, while their antimatter counterparts annihilated away. The vacuum, in this scenario, acts like a cosmic casino where the roulette wheel wasn't perfectly balanced and matter walked away with the jackpot. But Sakharov's final condition is the wild card, a universe out of equilibrium. For matter to win decisively, the process couldn't unfold smoothly. Imagine trying to bake a cake while constantly stirring the batter. You'd never get distinct layers. Similarly, without a sudden phase transition like the vacuum, freezing, from a high-energy state to a lower one, any matter-antimatter asymmetry would have simply re-equilibrated into oblivion. This is where the Higgs field's pivotal role comes into play. As the early universe cooled, the Higgs vacuum expectation value shifted dramatically, a phase change akin to water crystallizing into ice. This transition could have locked in the matter bias like a snapshot, preserving the tiny asymmetry long enough for it to shape the cosmos, the stunning implication. The quantum vacuum might not just host particles and forces, it could be the ultimate arbiter of existence itself. Without its subtle lopsidedness, matter and antimatter would have annihilated perfectly, leaving behind a sterile sea of photons. No stars, no planets, no us. Experiments like those at CERN-LHC are now hunting for signs of additional CP violation beyond the standard model, while neutrino observatories probe whether these ghostly particles might have catalyzed the imbalance. Even gravitational wave detectors listen for echoes of those primordial phase transitions when the vacuum structure shuddered and settled into its current form. What's awe-inspiring is how fragile this balance seems. Tweak the vacuum's CP violation by a fraction, and the universe either ends up empty or so dense with matter it collapses back into a singularity. It's as if the vacuum didn't just allow matter to dominate, it chose to with a precision that borders on the miraculous. Whether this was sheer luck, the hand of a multiverse, or something deeper we've yet to uncover, one thing is clear: the quantum vacuum isn't just the backdrop of reality. It's the unseen sculptor carving asymmetry into the very bedrock of existence. Loop quantum gravity dares to imagine a universe where space-time isn't just grainy, it's woven together like fabric on a cosmic loom. Unlike the chaotic froth of quantum foam, this theory proposes a vacuum made of intricate spin networks, minuscule loops of gravitational field that interlock to form the very architecture of reality. Picture the universe as a vast dynamic mesh where each thread carries a quantum of area or volume, stitching together a tapestry so fine it defies the infinite densities of black holes and the Big Bang itself. This isn't just tweaking the rules, it's rebuilding space-time from the ground up. At the heart of this radical vision lies the spin network, a mathematical web where each link represents a quantum of space, and each node marks where these quanta intersect. These aren't static structures, they vibrate, evolve, and reconfigure over time, creating what we perceive as the smooth continuum of space-time. It's as if the universe runs on a quantum computer, with spin networks processing reality at Planck-scale resolutions. Unlike the unpredictable foam of traditional quantum gravity, loop quantum gravity offers a precise, almost pixelated vacuum where infinities simply can't arise. No singularities, no endless curvature, just finite, discrete building blocks clicking into place. This granularity could be the key to some of physics' most vexing paradoxes. Take black holes. In Einstein's relativity, their cores crush matter into an infinitely dense point. But in loop quantum gravity, the spin network's tight weave prevents total collapse. Instead of a singularity, you'd hit a quantum bounce, a moment where gravity's crushing grip reverses, like a spring compressed to its limit. Some theorists suggest this could transform black holes into white holes, spewing out matter in a cosmic rebirth. The information swallowed by the black hole wouldn't vanish. It'd be encoded in the scrambled spin networks near the core, potentially resolving Hawking's infamous information paradox. Yet the theory doesn't escape controversy. Critics argue that spin networks, while elegant, lack experimental support, unlike quantum foam's indirect hints from black hole thermodynamics. Others question whether loop quantum gravity can truly reconcile with quantum field theory, or if it merely shifts the problem into new mathematics. Even the notion of a bouncing singularity raises eyebrows. If a black hole rebounds, where does the energy go? Could the vacuum itself absorb the shock, or would it birth an entirely new universe in the process? What's undeniable is how loop quantum gravity reframes the vacuum's role. Here, emptiness isn't a stage, it's the actor, an active lattice that vibrates, twists, and stores information like a cosmic hard drive. If spin networks are real, then every collision of particles, every warp in spacetime, is just a ripple in this deeper structure. The vacuum becomes not just the absence of matter, but the scaffolding of existence, whispering that the universe's true language might not be fields or particles, but the hum of a quadrillion spinning loops. The debate between quantum foam and spin networks isn't just academic, it's a clash of philosophies. Foam revels in chaos, viewing spacetime as a turbulent sea where wormholes flicker and causality blurs. Loop quantum gravity craves order, offering a vacuum where every quantum of space has its place. Which one paints the truer picture? Perhaps the answer lies in a synthesis yet to come, a theory that marries the foam's wild creativity with the spin network's rigorous geometry. Until then, the vacuum remains the ultimate mystery, its secrets locked in the dance between the infinitesimal and the infinite. The human brain remains one of the most complex structures in the known universe, a 3-pound web of neurons firing in patterns that give rise to consciousness itself. But what if there's more to this miracle of biology than biochemistry and electrical impulses? Some daring theorists propose that the quantum vacuum, that seething sea of virtual particles and fluctuations we've explored, might play an active role in the theater of the mind. This radical idea, often called the quantum mind hypothesis, suggests that consciousness could emerge not just from neurons, but from their interaction with the vacuum's deepest layers, blurring the line between thought and the fundamental fabric of reality. At first glance, the notion seems lifted from science fiction. The brain is warm, wet, and noisy, hardly the pristine environment we associate with delicate quantum phenomena. Yet certain features of neural processes bear eerie resemblances to quantum behavior. Take microtubules, the tiny protein structures inside neurons that some researchers believe could maintain quantum coherence long enough to influence consciousness. Theories like orchestrated objective reduction, ORC, or proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hamroff, argue that these microtubules interact with the quantum vacuum's fluctuations, collapsing wave functions in a way that generates moments of awareness. It's as if every thought might be a duet between neurons and the void itself. The vacuum's role in this dance would be subtle but profound. Virtual particles popping in and out of existence near synapses could theoretically influence the timing of neurotransmitter releases, adding an element of quantum randomness to decision-making. Some models even suggest the brain might harness zero-point energy, the vacuum's lowest energetic state, to power certain processes more efficiently than classical chemistry allows. These ideas remain firmly in the realm of speculation, but they raise a tantalizing question. Could consciousness be nature's way of listening to the quantum whispers most matter ignores? Skeptics rightly point out the lack of concrete evidence. The brain's environment seems hostile to sustained quantum effects with decoherence, the breakdown of quantum states occurring almost instantly at biological temperatures. Yet intriguing anomalies persist. Studies on anesthesia reveal that certain drugs seem to switch off consciousness by affecting microtubules specifically, hinting at a deeper layer of organization. Meanwhile, experiments with quantum coherence in photosynthesis show biological systems can exploit quantum effects. So why not neurons? The challenge lies in distinguishing genuine quantum biology from wishful thinking wrapped in mathematical hand-waving. Perhaps the most provocative implication is existential. If consciousness somehow taps into the vacuum's quantum substrate, then our inner experiences might be more than byproducts of neural computation. They could reflect a universe fundamentally tuned to observe itself. Philosophers have long pondered why subjective experience exists at all. The quantum mind hypothesis offers a poetic answer because the vacuum is restless and thought is its ripple. Whether this idea survives rigorous testing or fades into scientific footnote, it reminds us that the boundary between mind and cosmos may be far thinner than we ever imagined, and that the quantum vacuum, already the architect of matter and energy, might hold secrets about awareness itself. What if everything we perceive, every particle, every force, even the fabric of space-time itself, is nothing more than a hologram? This is the startling premise of the AD-S/CFT correspondence, a theoretical framework so revolutionary it suggests the three-dimensional universe we know might be a projection from a two-dimensional boundary, like a cosmic version of a credit card security hologram. At the heart of this idea lies a tantalizing possibility. The quantum vacuum, with all its seething fluctuations and virtual particles, could be the canvas on which reality is painted, with gravity emerging as a kind of quantum illusion. The AD-S/CFT correspondence was born in 1997 from the mind of physicist Juan Maldaisner, who sought to bridge the chasm between general relativity and quantum mechanics. His breakthrough came from studying a special type of spacetime called anti-de Sitter space AD-S, a universe with negative curvature where gravity behaves in peculiar ways. Maldaisner proposed that this warped spacetime could be perfectly described by a lower-dimensional quantum field theory living on its boundary, a concept known as the conformal field theory (CFT). In simpler terms, everything happening inside this hypothetical universe, stars, black holes, even the vacuum's quantum froth, could be encoded on its outer edge without losing any information. To grasp this, imagine a room where every object, every event, is actually a pattern of data projected from the walls. The three-dimensional world you perceive isn't real in the traditional sense. It's a dynamic hologram generated by interactions on the two-dimensional surface. Similarly, the AD-S/CFT correspondence suggests that the vacuum's infinite complexity, from virtual particles dancing in empty space to the bending of spacetime by gravity, might all derive from quantum information encoded on a distant boundary we can't directly observe. The implications for quantum gravity are staggering. One of the biggest hurdles in physics is reconciling Einstein's smooth, continuous spacetime with the jittery, probabilistic world of quantum mechanics. But if gravity is simply the holographic projection of quantum entanglement on the boundary, as some interpretations suggest, then the conflict dissolves. Black holes, those infamous destroyers of information, become elegant puzzles. Their event horizons might store all the data of what fell inside, like a cosmic hard drive, with the vacuum acting as the medium translating that data into the gravitational forces we observe. This holographic principle doesn't just reshape our understanding of gravity, it redefines the nature of reality itself. If the vacuum is the projector of the universe, then the distinction between empty space and matter blurs. Particles could be excitations of the vacuum's underlying quantum code, their properties determined by how information is processed on the boundary. Even time might lose its fundamental status, emerging only as a secondary effect of deeper quantum computations. Yet for all its elegance, the AD-S/CFT correspondence remains just that, a correspondence. We don't live in anti-de Sitter space. Our universe is closer to a de Sitter space with positive curvature driven by dark energy. Adapting Maldaisner's insights to our cosmic reality is an ongoing challenge, but tantalizing clues suggest the holographic principle might still hold. For instance, the way quantum entanglement seems to stitch together spacetime in our universe mirrors the boundary dynamics of AD-S/CFT, hinting at a universal pattern. Experiments to test these ideas are in their infancy, but some proposals look for holographic fingerprints in cosmic microwave background data or through quantum simulations using ultra-cold atoms. Others speculate that if the universe truly is a hologram, there might be fundamental limits to how precisely we can measure space and time, a pixelation of reality that future instruments could detect. What's truly mind-bending is how this theory transforms the vacuum from a passive backdrop into the universe's master programmer. The quantum fluctuations we've explored throughout this journey, virtual particles, zero-point energy, even the Higgs field, might all be surface-level ripples of something far deeper, a cosmic algorithm running on the fabric of spacetime itself. The holographic vacuum doesn't just host reality, it might be writing the script. Einstein's speed limit, the cosmic rule that nothing can outpace light, might not be as ironclad as we once thought. In 1994, physicist Miguel Alcubierre proposed a theoretical loophole so audacious it sounds like pure science fiction. A warp drive that doesn't propel a ship through space, but instead manipulates spacetime itself, riding a wave of compressed and expanded vacuum to effectively achieve faster-than-light travel. The trick lies in twisting the fabric of reality so that space ahead of the vessel contracts while space behind expands, creating a bubble where the ship sits motionless relative to its local spacetime, yet hurtles forward at speeds that defy relativity's constraints. It's like surfing a cosmic tsunami where the wave moves faster than light, but the surfer never breaks the rules, the engine fueling this wild ride. The quantum vacuum's own energy. Alcubierre's math suggests that to warp spacetime this dramatically, you'd need to harness something called negative energy, a bizarre form of vacuum energy that repels rather than attracts. Picture the vacuum as a rubber sheet. Normal matter dimples it inward with gravity, but negative energy would create a hump pushing spacetime outward. By surrounding a spacecraft with a ring of this exotic vacuum energy, you could theoretically contract space in front of you and expand it behind, bending the universe to your will while the ship coasts inside a pocket of flat spacetime. No G-forces, no time dilation, just the stars stretching and squeezing around you. But here's the catch: the energy costs are cosmic. Early calculations estimated you'd need the equivalent of Jupiter's mass converted entirely into energy, and that's before accounting for the staggering amounts of negative energy required, which may not even exist in sufficient quantities. Worse, quantum field theory hints that such a warp bubble could be catastrophically unstable. The moment you try to form it, vacuum fluctuations at the edges might amplify uncontrollably, releasing a torrent of high-energy particles that vaporize the ship or collapse the bubble faster than you can say engage. Some models even suggest the warp drive could trap Hawking radiation inside the bubble, cooking everything within like a cosmic microwave. Yet recent breakthroughs have chipped away at these obstacles. Physicists like Harold Sonny White at NASA Eagleworks lab have toyed with altering the warp bubble's geometry, reducing the energy needs from planetary scales to something closer to a small moon's mass, still impossible by today's standards, but less laughably so. Others speculate that Casimir cavities, nanoscale gaps where the vacuum's quantum fluctuations produce negative energy, might one day be scaled up or harnessed in arrays. And if dark energy's repulsive gravity shares properties with the negative energy needed, the universe itself might be offering clues on how to mine it. The most tantalizing and terrifying implication: warp drives might not just break the light barrier, they could shatter causality. A ship arriving before light would create paradoxes, messages from the future, events preceding causes. Some theorists argue quantum mechanics might enforce a chronology protection mechanism, where vacuum fluctuations grow infinite at the moment of paradox, shredding the warp bubble like cosmic immunity. Others propose wormholes or entangled particles could stabilize the timeline, turning faster-than-light travel into a tightly regulated cosmic subway. For now, Alcubierre's drive remains a dazzling thought experiment, a reminder that the vacuum's secrets might rewrite more than just particle physics. If we ever crack its code, the stars wouldn't just be within reach, they'd be next door. Until then, the quantum vacuum keeps its most revolutionary tricks just out of grasp, teasing us with glimpses of a universe far stranger than we dreamed. Empty space feels cold, so cold that even the darkest, remotest voids of the universe rarely dip below -270 degrees Celsius. But here's the paradox: the quantum vacuum isn't truly cold at all. Lurking beneath its icy facade is a hidden heat, one that only reveals itself to observers daring to push the limits of motion or gravity. This revelation shatters the classic notion of temperature, proving that warmth and chill aren't absolutes, they're deeply personal experiences shaped by how you interact with the vacuum itself. Take the Unravel effect, a phenomenon where acceleration conjures heat from nothingness. Imagine strapping into a rocket so powerful it could sustain a constant acceleration of 1,000,000,000 meters per second squared, an inhuman G-force beyond anything our bodies could survive. To an outside observer, your surroundings would seem frigid and empty, but from your perspective, the vacuum would glow with thermal radiation, registering a detectable temperature. The faster you accelerate, the hotter this phantom heat becomes, as if the universe itself were pressing a warm towel against your forehead. This isn't just theoretical, it's a direct consequence of the quantum vacuum's restless fluctuations. Virtual particles that usually cancel each other out get stretched apart by your violent motion, leaving some stranded as real photons. The result, a bath of warmth born purely from your own movement through the void. Hawking radiation offers a similarly twisted take on temperature, this time tied not to speed but to gravity's grip. Near a black hole's event horizon, the vacuum's virtual pairs get tugged apart by tidal forces, with one particle escaping as radiation while the other plunges into oblivion. To a distant observer, this radiation carries a precise temperature inversely proportional to the black hole's mass. Smaller holes burn hotter, like cosmic embers flickering against the dark. But cross the horizon and the story flips. From inside, the vacuum's temperature vanishes, there's no heat, just the crushing silence of singularity ahead. This duality forces us to confront a radical idea. Temperature isn't an intrinsic property of space, but a relationship between the observer and the vacuum's hidden structure. The implications for thermodynamics are staggering. Normally, heat flows from hot to cold until equilibrium is reached, but what happens when the vacuum's temperature depends entirely on how you're moving or where you're standing? Systems in strong gravitational fields or extreme acceleration might experience heat flow that defies classical intuition, like energy appearing to teleport across gaps or entropy decreasing in localized pockets. Some theorists even speculate that these effects could power future propulsion systems, where spacecraft manipulate local vacuum temperatures to harvest energy from spacetime itself, though the engineering hurdles remain firmly in the realm of speculation. Quantum information theory takes the puzzle further. If Hawking radiation carries data about what fell into a black hole, as modern physics suggests, then the vacuum's temperature isn't just a curiosity. It's a cryptographic key encoding the universe's deepest secrets. Entangled particles born from vacuum fluctuations near horizons might store information in their thermal properties, creating a cosmic backup drive that preserves the past even as black holes evaporate. This interplay between heat, gravity, and data could unlock new paradigms in quantum computing, where temperature gradients replace electric currents as the medium for processing information. Yet the most profound insight lies in how these effects blur the line between existence and perception. The vacuum doesn't have a single, true temperature. It's a chameleon, presenting warmth or cold based on who's looking and how they're moving. A planet orbiting a black hole, a spaceship accelerating relentlessly, and a lab on Earth would all report different readings for the same patch of nothingness. This relativity of heat challenges our most basic assumptions about reality, suggesting that even something as fundamental as temperature might be a cosmic illusion, one more card in the quantum vacuum's endless deck of tricks. What if every time you blinked, the universe split not metaphorically, but physically into countless parallel realities where every possible outcome plays out simultaneously? This startling idea lies at the heart of the many worlds interpretation of quantum mechanics, where the vacuum doesn't just host particles, it acts as the ultimate branching machine, spawning new timelines with every quantum fluctuation. But here's where it gets eerie. If the multiverse is real, could the quantum vacuum be conspiring to keep you alive indefinitely? This is the unsettling premise of quantum immortality, a thought experiment where the mere act of observation might tether you to timelines where death, statistically inevitable, somehow never arrives. Imagine a modified version of Schrödinger's cat experiment, but instead of a feline in a box, it's you with a trigger linked to a quantum event, like a radioactive atom decaying. In one branch of reality, the atom decays and the mechanism fires. In another, it doesn't, and you survive. Many worlds suggests both outcomes happen, splitting the universe into two streams. But here's the twist. From your subjective perspective, you can only experience the timelines where you're still alive. Every time the trigger pulls, your consciousness hops to a reality where the gun didn't fire, creating the illusion of miraculous survival. The vacuum, in this view, isn't just empty space, it's an infinite loom, weaving a tapestry of realities where you persist against all odds. This isn't just philosophical sleight of hand. The math of quantum decoherence, the process where probabilities collapse into definite states, shows that observers become entangled with their environments, including the vacuum's fluctuations. In a branching multiverse, your continued existence isn't luck. It's a logical necessity. Of course, this raises thorny questions. Why would consciousness favor survival? Could someone test immortality by repeatedly risking their life, trusting the universe to shunt them into the timeline where they narrowly escape? The grim reality is that while your subjective experience might feel continuous, countless versions of you in alternate branches wouldn't be so fortunate. Critics argue this reduces to solipsism, the idea that only one's own mind is sure to exist. After all, if consciousness cherry-picks realities, why do we witness tragedies at all? Some interpretations suggest quantum immortality only works for deaths tied to quantum randomness, not mundane risks like aging or disease. Others propose that the illusion breaks down when all possible branches lead to demise, forcing the observer's experience to simply end. Yet the idea lingers, forcing us to confront the vacuum's role as reality's ultimate randomizer. Every virtual particle's flicker, every fluctuation in the zero-point field, could be a fork in the road of existence, a silent arbiter of who lives, who dies, and who keeps perceiving the universe's unfolding story. Whether you find this thought liberating or terrifying, one thing's certain: the quantum vacuum doesn't just underpin matter and energy, it might just be the architect of destiny itself. Sound might seem like the last thing you'd associate with the vacuum of space. After all, there's no air to carry vibrations. But in a lab in Israel, scientists have created something astonishing: a black hole for sound, where the quantum vacuum's whispers take on an eerie new form. By chilling rubidium atoms to near absolute zero and trapping them in laser fields, they've crafted a bizarre state of matter called a Bose-Einstein condensate, a fluid so cold and dense that sound waves move through it like light through space-time. And just as a black hole's gravity traps light, these sonic black holes can trap sound waves behind an inescapable sonic horizon. The result: a laboratory playground where phonons, quantized sound particles, mimic Hawking radiation, offering a tantalizing glimpse into how quantum fields behave near real black holes. The key lies in the condensate's fluid dynamics. When stirred to supersonic speeds, the fluid creates a region where sound waves trying to escape get dragged backward, just like light near an event horizon. At the boundary between subsonic and supersonic flow, quantum fluctuations in the fluid spawn pairs of phonons, one falling inward, the other radiating outward as thermal noise. This is the sonic analog of Hawking radiation, with the vacuum's quantum jitters playing the same role as virtual particle pairs near a black hole. The math governing these phonons is eerily similar to the equations describing photons escaping a collapsing star, suggesting that the vacuum's behavior isn't just a cosmic curiosity. It's a universal pattern repeating across scales. In 2019, researchers at the Technion in Haifa observed this phonon radiation directly. By carefully tuning the condensate's flow, they detected the faint thermal signature of escaped phonons, a smoking gun for analog Hawking radiation. The temperature matched predictions down to the nanokelvin, providing the clearest evidence yet that spacetime's most exotic phenomena can be recreated in a tabletop experiment. But the implications go far beyond a cool lab demo. If sonic black holes radiate like real ones, it bolsters the case that Hawking's theory isn't just mathematical poetry. It's a fundamental feature of how quantum fields interact with horizons, whether they're made of gravity or superfluid vortices. What's even wilder is how this ties back to the quantum vacuum's hidden music. Just as empty space crackles with virtual particles, the Bose-Einstein condensate buzzes with quantum sound phonons that exist only as fleeting fluctuations until the fluid's horizon teases them into reality. Some theorists speculate that similar sonic horizons might exist in neutron star cores or quark-gluon plasmas, where extreme densities could create acoustic black holes in nature. Others wonder if the universe itself, in its earliest moments, behaved like a superfluid, with quantum sound waves seeding the large-scale structure we see today. These experiments aren't just about black holes, they're a masterclass in universality, showing how the vacuum's quantum rules echo across wildly different systems. Whether it's photons battling gravity or phonons fighting fluid flow, the same underlying physics emerges, hinting at a deeper harmony woven into reality's fabric. And with each new analog black hole crafted in a lab, we get closer to answering the haunting question: if the vacuum sings the same song everywhere, what else might we learn by listening? The universe might owe its existence to the ultimate quantum gamble, a random vacuum fluctuation so rare that it birthed everything from nothing. Imagine the void before time, a realm not of empty blackness but of restless potential. According to quantum cosmology, even in the absence of matter, space, or time, the vacuum's inherent uncertainty could have spawned a bubble of space-time that inflated into our cosmos. It's as if reality won the lottery against impossible odds, with the quantum vacuum playing both the ticket and the hand of fate. This idea that the Big Bang was sparked by a spontaneous quantum event turns traditional cosmology on its head. Instead of asking what existed before the universe, we're forced to reckon with a deeper question. Can before even have meaning when time itself is part of the cosmic aftermath? In quantum terms, the vacuum isn't nothing in the philosophical sense. It's a roiling foam of probabilities where energy borrows from itself, debts paid back in fractions of a second. Under these conditions, a fluctuation vast enough to create a universe isn't prohibited, just extraordinarily unlikely. The math suggests it could happen once in 10 to the power of 10 to the 120 years. But given infinite time or no time at all, statistics cease to matter. Yet this radical vision isn't the only contender. Cyclic models propose a cosmos without true beginnings or endings, just endless cycles of expansion and contraction, each Big Bang followed by a big crunch. Here, the vacuum isn't a creative fluke but a recurring stage, resetting itself like a cosmic accordion. Imagine the universe breathing in and out, matter dissolving into energy, space collapsing to a singularity, only to rebound in a new explosion. These models sidestep the something from nothing paradox by making the vacuum eternal, a backdrop that outlasts any single iteration of reality. The tension between these ideas exposes the murkiest puzzle in physics. What exactly is nothing? Quantum fields buzzing with zero-point energy, a void beyond spacetime. Even the language betrays us. Words like arose or before imply a timeline that may not apply. Some theories, like the Hartle-Hawking no-boundary proposal, suggest the Big Bang wasn't an explosion in time, but a smooth geometric transition where time and space crystallized simultaneously from a four-dimensional quantum fog. Others posit that our universe is one bubble in an infinite multiverse foam, each with its own laws born from separate fluctuations, the most unsettling implication. If the universe emerged from a vacuum fluctuation, it could happen again anywhere, anytime. A new bubble of spacetime might nucleate in the void beyond our cosmic horizon, inflating at light speed to overwrite our reality before we'd ever see it coming. Or perhaps it already has countless times in regions forever cut off from our view. The vacuum doesn't care about permanence, only possibility. And in that infinite potential, our existence is both miraculous and mundane, one roll of the dice in a game without end. The quantum vacuum isn't just a scientific curiosity, it's a frontier brimming with revolutionary potential, waiting to rewrite the rules of energy, space, and even the nature of reality itself. Imagine a future where we don't just study the vacuum's quirks but harness them, turning its hidden energies into power sources that defy conventional physics. Take the Casimir effect. Those phantom forces pushing metal plates together could one day drive microscopic engines, their pistons powered not by steam or combustion but by the ceaseless jitter of virtual particles. Researchers are already exploring nanoscale devices that exploit this phenomenon, where the vacuum's relentless fluctuations become the ultimate renewable resource, a battery that never depletes because it taps into the fabric of spacetime itself. But the real game changer lies in spacetime engineering. If we can manipulate vacuum energy at scale, the implications stretch far beyond Earth. Warp drives, once confined to sci-fi, enter the realm of possibility if we decode how to stabilize negative energy densities, those bizarre repulsive forces hiding in the quantum foam. Picture a spacecraft enveloped in a warp bubble, its path carved not through space but by bending the vacuum's structure. The energy hurdles are astronomical, but breakthroughs in metamaterials or quantum field control could one day make this feasible. Even a modest success would revolutionize interstellar travel, shrinking the vastness of the cosmos into something navigable within a human lifetime. Then there's the most speculative and tantalizing frontier, the vacuum's role in consciousness and reality's deepest layers. Some theorists propose that the brain's microtubules might interact with vacuum fluctuations, suggesting that subjective experience itself could emerge from quantum processes woven into empty space. If true, mastering these interactions could unlock technologies that merge mind and machine at a fundamental level, or even reveal that the universe is a computational matrix running on the vacuum's quantum substrate. Experiments in quantum biology and lab-grown neural networks are already probing these edges, seeking traces of vacuum-level influences on thought and perception. The vacuum's secrets might also hold the key to unifying physics' greatest theories. A full understanding of zero-point energy could bridge quantum mechanics and general relativity, exposing hidden symmetries or extra dimensions that reshape our cosmic blueprint. Projects like quantum gravity detectors and next-gen particle colliders are inching closer, hunting for anomalies in vacuum behavior that hint at these deeper laws. And if the holographic principle proves true, that reality is a projection from a two-dimensional boundary, then the vacuum isn't just a medium but the universe's operating system, its code waiting to be decrypted. This isn't just about futuristic tech, it's a paradigm shift in how we perceive existence. The vacuum's mysteries challenge the very notion of nothingness, suggesting that everything we see, matter, forces, even time, might be emergent properties of an underlying quantum tapestry. As research accelerates, the line between science and philosophy blurs. Are we on the brink of harvesting limitless energy, bending space-time, or even uncovering the universe's source code? The answers won't come easily, but one thing's certain: the quantum vacuum is the ultimate playground for the next century of discovery, and its revelations could dwarf everything we've learned so far. The void, it seems, is just the beginning. The quantum vacuum seems to be the ultimate foundation, the silent stage upon which all particles and forces perform. Yet after exploring 29 astonishing mysteries, we're left staring at the most profound question of all. Is this vacuum truly fundamental, or is it just the surface of something far stranger? Imagine peeling back the layers of reality only to find that what we call nothing is actually a veil, hiding dimensions or structures beyond our current comprehension. This isn't just philosophical musing, it's a puzzle that could rewrite physics. Take string theory's radical proposal. The vacuum we know might be a three-dimensional brain floating in a higher dimensional bulk. In this view, the particles and forces we observe are just vibrations trapped on our brain, while gravity, notably weaker than other forces, leaks into the bulk. The vacuum's deepest fluctuations could then be echoes from these hidden dimensions, like ripples hitting the surface of a pond from below. If true, it would mean everything we've ever measured, every quantum effect, every flicker of virtual particles, is just a shadow of a richer, multidimensional reality. But string theory isn't the only contender. Loop quantum gravity suggests the vacuum might be woven from discrete, finite loops, a pixelated spacetime where continuity is an illusion. Some versions of quantum field theory even propose that what we perceive as empty space is a condensate, analogous to how water vapor condenses into liquid. Just as liquid properties emerge from collective molecular behavior, the vacuum's properties might arise from an underlying quantum substrate we've yet to identify. The stakes couldn't be higher. If the vacuum is fundamental, then our current theories, however incomplete, are at least probing the right level of reality. But if it's emergent, then everything we know is akin to studying ocean waves while ignoring the water itself. Experiments at the Large Hadron Collider and future quantum gravity detectors aim to settle this by hunting for subtle deviations in vacuum behavior, tiny anomalies that could betray the presence of hidden layers. Even the faintest whisper of extra dimensions or space-time granularity would revolutionize our understanding of existence. Perhaps most tantalizing is the possibility that the vacuum's greatest secret isn't a thing, but a process, an algorithm or computation unfolding beneath the surface. Some digital physics theories argue that the universe operates like a quantum computer, with the vacuum acting as its processing substrate. In this scenario, particles and forces are the outputs, while the code runs on a deeper, information-theoretic layer. It's a wild idea, but one that gains traction every time we discover new parallels between quantum mechanics and information theory. So where does that leave us? The vacuum, for all its mysteries, remains the ultimate mirror reflecting back whatever assumptions we bring to it. Whether it's the final foundation or just another stepping stone, one thing's certain: the closer we look, the less empty it seems. And somewhere in that paradox lies the next great leap in our understanding of reality, a leap that might not just explain the universe but redefine it entirely. From virtual particles flickering in the void to black holes leaking secrets through Hawking radiation, the quantum vacuum has proven itself to be anything but empty. These 30 mysteries aren't just curiosities, they're cracks in the foundation of reality, offering glimpses into a hidden layer of existence where the rules we know begin to unravel. The vacuum isn't merely the backdrop of the universe, it's the architect shaping everything from the mass of particles to the expansion of spacetime itself. What makes this frontier so electrifying is how each discovery peels back another layer, revealing deeper questions. The Casimir effect shows us that nothingness can push objects together. Vacuum fluctuations suggest particles can appear from nowhere. Even concepts as fundamental as time and gravity might emerge from the vacuum's chaotic dance. This isn't just about filling gaps in our knowledge, it's about realizing that what we call reality might be a thin veneer over something far stranger. The implications are staggering. If we could truly harness vacuum energy, we might unlock power sources beyond our wildest dreams. If we decode spacetime's holographic nature, we could rewrite the laws of physics. And if the multiverse theory holds, the vacuum might be the loom weaving infinite realities into existence. This isn't science fiction, it's the cutting edge of human understanding, where the line between philosophy and physics blurs into awe. So where do we go from here? The quantum vacuum challenges us to rethink everything we thought we knew. It's a puzzle with no final piece, a frontier where every answer births new mysteries. And that's what makes it the most exciting playground in science. Which of these 30 mysteries fascinates you the most? Is it the phantom pull of the Casimir effect, the chilling possibility of vacuum decay, or something else entirely? Drop your thoughts in the comments, because the greatest discoveries often start with a simple question. Let's unravel the secrets of